Okay, let's take a look at the first problem. It's a problem asking you to solve this unconstrained optimization with a starting point, where A being your last digit of your phone number. In my case, it's 7, and B being the month of your birthday. In my case, it's 2. And we're going to solve until the error is smaller than 10 to the power of negative 3. And the problem asks you to use conjugate gradient method and use finite difference to solve for the derivatives. So um, very similar to what we did in the past, but um, we are this time using conjugate gradient. So I'm using my MATLAB code to demonstrate what happened. I'm making a pause right here. As you can see, my objective function is already written based on my phone number and my birthday. This is my starting point. I'm choosing some delta, which is I think is small enough. You already have 4 zeros after the dot. Should be accurate enough. So let's run the code and then let's go through what's going on inside the conjugate gradient code. So here's my objective function, my initial guess, my small delta, and then let's continue to take a look. So in my code, I'm setting k as my iteration number. I have to start with 1 because MATLAB doesn't allow index number with 0. So uh, my x 1, the first one, is basically our initial start. I'm choosing a large error value. This is for plotting. So over here I plot out the objective function. I plot out where the point is. I display some information at the beginning. I even did the function call. So over here, starting from the loop, here's where we use finite difference. So you need to evaluate your objective function value at your uh, design point. Basically, right now it's -5 and -5. So I substituting my objective function, my design variable into the objective function. Okay, so that the value is 634, something like this. So how do you do finite difference? This time when I substitute, I add a small value to x1. So delta is 10 to the power of -5, multiplying 1 and 0. So basically the first variable will be increased by a little and use that. So it's basically, what is this? Let me show you. It looks the same, but it's actually the issue of MATLAB displaying. It's actually uh, not -5. So this is just after rounding, you don't see it. So let's plug in and take a look. You can see in MATLAB this is symbolic result, but I can evaluate the function value and let you see. It's actually 633 point something compared to the objective function value at -5 and -5. It's slightly different. That's a key. There's a slight difference. Then you can evaluate the derivative. Do the same for the partial f partial x2. Now, following the for scheme of finite difference, you can compute for. No, sorry, that was just a evaluation at uh, your design variable with small increment on x2. So this is for finite difference. Okay, so after that you can get partial f partial x, and this partial f partial x1, partial f partial x2. So that's your gradient. Okay, so let's get those done. So your gradient is like this. If you want to see the value, this is the gradient. Okay, so in our figure, gradient is like a negative 24 and negative 140. So it's like going this way. So in optimization, we would like to move along the negative gradient direction. So conjugate gradient will try to move along this direction toward upper right. Okay, now we need to do line search. So over here, I chose to have a initial gas of 1. So my A is my alpha. M is the index for the iteration number for the line search. So for conjugate gradient equation, when we are at the first iteration, our direction is just a negative gradient right here. Okay, so this is our negative gradient. Now how that we need to formulate the x in terms of our alpha. So A is a symbolic variable. So capital A is the not values that we make gases, but small a is the symbolic function. So here, this is my current variable. A is just a symbolic a. Gradient, basically, the direction is negative gradient. So just put them together. What do you have? You have a function of, let me show you. So it's symbolic. You can say evaluate x underline a. It doesn't, yeah, because a is still symbolic. So basically, you have a vector in terms of unknown alpha. You just need to know what the alpha is. Then you can evaluate for the x. So let's keep it like that. It's the xa x alpha is a symbolic x. Later on we are going to use it. So keeping the memory. So all the gradient is like this. Keeping a memory. All direction is like this. Keeping them. And then over here you will need your objective function in terms of your unknown alpha. So just substituting into your function f. Okay, so after substituting, your f alpha is again a bunch of values with undetermined alpha. If I try to simplify it, it's already this is the simplest form MATLAB can get. Okay, so over here your f now is a function of alpha. Okay, so we need a smaller while loop in order to determine the best alpha. So what does it mean? It means we are moving along this way, but we don't know how far we go. So alpha defines how far we go. Okay, so that's why alpha is called the step size. So over here you basically have initial gases. My initial gas alpha is 1, so you just plug in. So our objective function f was a function in terms of unknown alpha, so you just plug in your guess, which is 1. So I just plug in, move forward, and over here I'm using Newton's method, so I need to do a forward increment and a backward increment, like a decrement. So I have a plus delta on A and I minus delta on A. Plug those into our objective function in terms of unknown alpha. So after you plug in, you will get values. So after those, let's take a look. This is my you can evaluate those to see their real values. Okay, so if I plug in 1, if my alpha is 1, you have no idea where it is, but it's somewhere. This is the objective function value. And if I have basically alpha equals to 1 plus your delta, you have a different value. And you can see there's a slight difference. That's how you can get derivative. And let's take a look at the negative one. You can also see, yes, they are slightly different. Okay, so just follow finite difference. Use the 1 in the front minus the current one divided by delta. F double prime can be determined by the 1 in the front minus 2 times the current one plus the 1 in the back, divided by square of the delta. So do those. What will be the value? This is your f prime, some large value like this, and this is your f double prime. Okay, doesn't matter. Computer helps you to, your calculator, your computer helps you to compute. Okay, now follow the Newton's method's equation. Boom. It tells you initially your guess was 1, but after Newton's method it tells you, oh, it should be 0.0513, something like that. So you need to iterate. So over here you are using 0.0513 to do the same thing again. Now check the error. Error becomes very small. That's why you are out of the loop. So once you're out of the loop, your A, the last one, this one is your optimal alpha. So plug in back to your original equation here. Right? This is basically the same equation as this one. The idea is it's the same one, but now we update it to our variable for each iteration, which is the capital X. Plug in. So initially we started from somewhere here. So it's telling us to move somewhere to here. Okay, let's do the plotting. Yeah, it's asking us to move to that. Draw a straight line. Okay, the error is large, so it's not converged yet. Now let's move on to the next iteration. Do the same thing for the gradient evaluation. Now, because we're in the second iteration, we need to follow the conjugate gradient equation. Our direction is going to be negative gradient plus the norm of the current gradient divided by the norm of the previous gradient, and square of those times the previous direction. So just follow those, and we have a new vector. Okay, and the rest is the same. The rest is the same. again you do the line search. So I'm not going to go go through line by line. Just move to here. So it tells you to move to somewhere here. Now the error is 10, not yet converged. So do it again. It actually moved a little bit. It actually moved a little bit. Okay. Now let's take a look. What's the error? Error is not small enough yet. So one more iteration. So it moved a little bit more. What's the error? Okay, it's already smaller than 10 to the power of -3. So if we keep on moving, we satisfy the termination criteria, so we are out of the loop. And that's why it's finished. It's done. Okay, so that's the solution. 7 and some number very close to 2, but the real number should be 7 and 2. Okay, if you set up a even tighter convergence criteria, it's possible you can get there, but when you have even tighter convergence criteria, your gradient, your delta maybe needs to be even smaller. Okay, so that's the first problem. What's going on with the second problem? In the second problem, I'm asking you to use linear programming to solve a nonlinear problem. How can we do that? Because linear programming is only used for linear problems. So in this case, I show you a process flow to help you to understand what I'm looking for. So this is the problem where we have actually two constraints. These two are just variable bounds. So for linear programming, you just need to care about these two, and just making sure the x1 and x2 are positive all the time. So only two constraints, but the first constraint is nonlinear, second one is linear. The objective function is nonlinear. We're using the same a and b. Okay, so over here I'm telling you, start with your initial guess 0 0, and you need to perform Taylor expansion at 0 0. So the first objective function and the first constraint will be linearized by first order Taylor expansion. Then you can use linear programming to solve the problem. And let me show you how does it look like. Okay, so over here, my last digit of cell phone is 7, birthday 2. Right? So let's use this as a use my MATLAB code to show you what happened. So here's my objective function. Okay, you can compare. That's the objective function based on the given a and b. Constraint. So I already rewritten the equation g1 into such a form so that I want this to be smaller than 0. So I move everything to the left hand side. Okay, and g2 also I move everything to the left. So I'm making sure g2 is in a form such that it's smaller than 0, smaller or equals to 0. So forward. Now make some drawing. First, what I did was, what's going on with this? I use the function called the EasyPlot. EasyPlot is a function that can plot one-dimensional problem. So I need to say, because g1 is a two-dimensional function, so I just want to know what's the math function in terms of x2 equals to what. So if you say solve g1 and comma x2, it's going to tell you, okay, x2 equals to this. And if you compare, basically this is this, right? Because I'm drawing the boundary, so I'm drawing the limit state where x2 equals to the right hand side. And by MATLAB you can see, okay, that's the right hand side, and that's how the function look like. I'm just plotting it within a range from 0 to 10. Now I'm drawing the contour of the object function. Okay, so as you can see, inside the design space, if I move toward the upper right corner, the object function decreases. So that's where our solution should be, going upper right. And there's a boundary, and we x2 smaller than the right hand side, right? So underneath this curve is the feasible space. Above is infeasible. Okay. There's a G3. I didn't draw the G3 yet. G3 is, I should. Let me draw it. So G3 I'm sorry. G3 sorry, G2. I just need to draw the G2. So you can say easy plot solve G2 x2 and draw within the range. Yeah, that should be it. So okay. So is it on the left or right? Is it on the left or right? If you plug in 0 and 0, no matter what b you have, it's always 0. So it's always, so 0.00 is always giving you values that is smaller than 3. So it's always on the left of this red line. So here's the feasible space based on the A and B. Based on my phone number and birthday. For your case, the shapes will be different. So let me show you. If someone is having a different phone number, for example 4, and let's say someone is having a birthday at October, then as you can see, the shape changed a little bit. Okay, that's fine, it doesn't matter. It's still a solvable problem. Now inside a loop, I'm going to, so in this case you need to do first order Taylor expansion, right? Let me go through the procedure. First order Taylor expansion, then do linear programming. Every time for the linear programming, start with 0 0. Basically it's like setting up the first two variable as non-basic, and at the end you will get an optimal solution. Set it as the new point. Check if the new point and the previous one is converged. If not, do it again. Go back to step 2. So it's going to be a sequence. You are going to perform B, C, D, B, C, D, B, C, D until that's satisfied. So it's actually a two-level process. Outer level is the iteration process over here. The inner loop is the linear programming. Okay, so now this is the outer loop. My linear programming is right here. We will go through that later. So let's come up here. Over here, this is how I perform first order Taylor expansion. So what I did was just follow the equation. You plug in your current x, plug into your objective function, and then plus your symbolic variable minus your current x times the gradient. Over here, I didn't say you have to use uh, finite difference or derivative. It's up to you. I don't mind. So here I'm directly using, for my MATLAB code, I'm using derivative directly. If I perform finite difference here, same result. I still can get it, but it really depends on how accurate my finite difference is. In the current video, I'm going to use DIFF, just direct derivative, making the partial derivative with respect to x1, plugging on my current value, plus x2 minus the current x2 times the partial derivative with respect to x2 and current value plugging. So that's how you get it. Let's take a look at how it looked like after you do this. So that's the linear function, linearized function. Okay, G, do the same thing. G1 was a nonlinear function. Do the same thing. What does the linearized G look like? It's a linear function like this. Okay. Now I'm making some plots to show you how the linearized function look like. So first I'm plotting. So same trick. I use solve capital G1 comma x2. So it helps me to draw a line. Okay, that's the line. Okay, as you can see, originally, let me just show you within the region I prefer. Originally, G1 was a curve. Now, after linear approximation, with 0, 0 as the expansion point, you have a approximated linear function, pretty close to the original function, but not exactly the same. So you can imagine, if I perform linear programming, I may find solution right here, but in fact the true solution is here. That's why we need a second round. Okay. Now, over here, what's CAB? Basically, I'm preparing for the linear programming. So over here, I'm just trying to get the coefficients. Like here, you need to negative 28 and negative 200. So over here, if you do that, your C becomes negative 28 and negative 200. I already know the problem needs slack variables, so I do already have the third one and the fourth one. Okay. For the A matrix, basically you are going to get the coefficients from G1, so negative 2 and 1 for the first row. Second row, basically it's gonna be based on your G2, so it's gonna be 1 and B over 50. Okay, so do that. I'm using derivative to get the coefficient. So step forward here. Like I said, my G1 was this, so I should get negative 2 and 1 for my first row of A. Negative 2 and 1, yes, first row of A. Now second row, here should be 1 and B over 50. B in this case is 10, so 10 over 50 is 0.2, so it should be 1 and 0.2. So second row is 1 and 0.2, right? 1.2. For the third column and the fourth column, they are 1, 0, 0, 1 because of our slack variables. Now how do you get B? B vector basically plug in to your G function and G1 and G2, but remember, this time we move the coefficient to the left hand side, but for the linear programming, you need coefficient on the right hand side. That's why I plug in I'm using 0, 0 to plug in and then put a negative sign here, so the value goes to the right hand side. Okay, yeah. So in the end, I should get positive 2.5 and positive 3. See, 2.5 and 3. So you can throw those into the linear programming, and I'm jumping in, step in. Okay, so here's my C, A, and B. This code is exactly just almost the same as what I had in the class, but I made slightly changes. So I'm making this more adaptive. So there's a variable called number of variables here. It's going to uh, give me numbers of the length of C. So basically now it's 4. There are 4 columns. In the basic, always, because I'm solving a 2D problem only. If it's a 3D problem, then it's different. The code has to be rewritten. So I'm treating the first 2 as non-basic, and the rest will be basic. So they are ones. So here is 0, 0, 1, 1, 1. So what's going on here? It's 0, 0, and 1, 1. So ones basically give you a bunch of numbers, a bunch of ones. It goes and length of C it's 4 minus 2. That's 2. So ones in a vector of 1, 2. So in the size of 1, 2. So they are all ones. That gives me 0, 0, 1, and 1 here. So basic is like this. First 2 are non-basic, the other 2 are basic. That's how you can start from 0, 0. Okay, then here I'm drawing the figure again, but this time it's a linearized objective function. Let me show you. So the curved one is the true objective function. The straight one is the approximated one. Okay. So it's a little hard to see, but it's you probably can tell. Okay, the curved one is original one. The straight one is the approximated linearized objective function. Now, okay, here is just for the plotting. In the code, it's plotting the same thing again, and then yeah. So over here, we are solving the 2 linear function as I mentioned, and you know the solutions here. Now follow the linear programming procedure. Here, I'm collecting what the basic ID, basically the 3 and 4, but I don't need a 0. I eliminate the first one, so 3 and 4. How about the non-basic? 1 and 2. Over here, I need to get CN, CB, AN, AB. So get those. So CN, two components, CB, AN, AB, just like what we did in the class. Now, initially, our x is like this. So first 2 variables are 0, and my x3 and x4 they are 2.5 and 3. Okay, plotting the initial guess. So from 0, compute the coefficient based from the notes Cn minus Cb times AB inverse times An. So over here we're going to find the most negative one, which is the second one. So over here, find the smallest one. Smallest ID is the second one. Is it positive? If it is, then we will stop the loop. If not, then okay, we can do it. It's negative. Okay, so the second one was chosen. Now here is just telling me which ID will be converted from non-basic to basic. So using this, the second one. So the second x2 will be converted from non-basic to basic. Now we compute A head and B head. So the ratio test only choose the jth column of A head, and J right now is the second one. So meaning ID is second one from A head. So for the ratio test, do this division over here. Okay, we are going to choose the smallest positive one. So the first one here. If there is one of the ratio that is negative, we push it to positive infinity, so it won't be chosen. Okay, now the ratio is still the same, 2.5 and 15. The first one has the smallest positive, so over here the chosen one is the first one. So the ID that to be converted from basic to non-basic will be the first one inside basic ID, which is 3x3. So now basic the conversion, the second one becomes 1, third one becomes 0. Boom, boom. Okay, that completes the first iteration. And moving forward, do the whole thing again, and it will show you the plot. That's where we are right now, here. And let's check the coefficient. Only one is negative, so that one will be chosen. And do the same thing again, do the ratio test. Right now the ratios are, one is negative, the other one is positive, so the negative one will become infinity from the code right here. The ratio now, the first one becomes infinity, so we won't choose that one. That's too large. That one is too large. So the second one inside the ratio will be chosen. Now do the swapping. After swapping, let's check where we are. We found the point at the intersection right here. That's the optimal for linear programming process, but it's based on the linear approximation at the beginning. So later on, when we go out, we will perform the Taylor expansion again. Hopefully we can get a better accuracy on the linear function. Then we can start over and get closer and closer. Now let's take a look at the last couple steps of linear programming. Over here, both the coefficients are positive, so you don't need to do linear programming anymore. You will go out and finish, right? So get back your out, and that's your solution. Originally we started from 0 0, and after the linear programming process we realized, okay, the solution is 1.7 and 6.0, which is this one. Okay, so you check this is the outer loop, you check the difference, the error is large, so you need to continue again, starting over. This is where we perform linear programming, Taylor expansion. So Taylor expansion again, plotting the G2. Okay, and I'm going to show you inside the region. So did you see there's a new line? Because we are pretty close to the solution, so the function will be more accurate when we are closer. So you can see the linear function, the new linear function, is pretty close to the curve. So I think in the second round this approximation is better, right? It's better than the first one. But if we are not getting closer, we cannot get this more accurate linear approximation. So do the same thing again, and let's see what's the solution. I'm not jumping into linear programming anymore. So in the second round of linear programming, it's starting from 0 again, going up to here, and directly comes to this one. Okay, it's getting closer to the true solution. And let's see the error. Still not small enough. So we need to go over again. Let's hope this time the approximation is very similar to the previous one, so we can get the same solution. Okay, we already plot out, but this time you don't really see a difference. We may need to zoom in. You don't, it's hard to tell. Okay, it's hard to tell. Let's do this. So this one was, let me turn off the line drawn by the by linear programming, and let me try to show you. Hold on. What's going on? Okay, so what happened was, at the first time, let me turn off the contour, objective function contour. At the first time, we were having, this one is the very first linear approximation. That's why we found a solution right there. The second time, we found a approximation right there. So let's get closer to realize. Okay, we are pretty close. And this is the true function. This one is the true function, the nonlinear one. And this one is the linear approximation from the second round. How about the linear approximation for the third round? It's right here. Did you see we're getting really close? Really close to the curved one. Okay? Good. So now let's get back. Maybe we just continue from here. You will go back to the original scale. Okay, I'm going to turn off some of the drawings here. Okay, and I'm zooming even more just to show you. Yeah, very good. So this one is the nonlinear function. This one is the linear approximation in the second round. So we got a solution here. This is the linear approximation for the third round. That's why the linear programming was able to find a solution here. So if we're close enough, we can converge. Let's check the error. Right now is pretty small actually. So the difference between this one and this one is very small. So converge. And that's the solution. Right here. So this is the solution. The last one. So what are my x? So you can see the last one is my solution. Okay, we started from 0, 0. we first go to this 1.7 right here. Let's get out. Let's get further. Okay, so we started from 0, 0. After first linear programming, we were here. Okay, after first linear programming, we were here. After second one, we were second linear programming, we were here. Third linear programming, we were here. So we have 3 rounds of linear solutions from linear programming. And in fact, the second round and the third round, even though from MATLAB it looks like they are having a distance, but this distance is very small, super small. So when you compute the norm between them, it's already smaller than 10 to the power of -3. So it converges. Okay, so that's it. That's how you can get this one. And shall we take a look at some different values and see what's going on? What will happen if I have, for example, in my case, cell phone number 7, birthday 2? What does it look like? Yeah, so the solution is right here. Okay, if I have, for example, cell phone number 0, birthday December, what does it look like? Same thing. You still can get a solution. Okay, so that's it for today. Hopefully you understand what's going on.